Okay, Algebra 2, we're going to move on into Chapter 13 now, which takes us back to trigonometry, which you guys spent a chapter studying last year in geometry. And we're going to get to it a little bit here and write it out through most of the end of the year. All of you guys who are taking pre-calculus next year, you're going to see a whole lot more trig at that level too. So trigonometry, when you break the word down, really just means the study of triangles, and specifically, we spend the majority of our time here dealing with right triangles. And if you recall, a right triangle is any triangle here that has a right angle indicated by this little thing here, that box that we call a corner mark. And the first thing we wanted to review here is just to kind of go back over the Pythagorean theorem, which you guys dealt with a lot last year. So the Pythagorean theorem, I prefer to write it in this manner right here. Leg squared plus leg squared is equal to hypotenuse squared, but I know that most of the rest of the world likes to write it this way. A squared plus b squared is equal to c squared. Now that second way right there, while not my favorite, it does completely work if, and here's a big if, guys, you understand the naming system that's used in a right triangle. So let's talk about that real quick. In a right triangle, the conventional way, meaning the way that most people agree to do it, but it's not a rule, it doesn't have to be done this way. The conventional way of naming a right triangle is to let the two acute angles, the ones whose measures are less than 90, be capital A and then capital B. Doesn't really matter which one of those is which, but what's really important right here is that the right angle is capital C. So that's naming those 3 points right here that define the vertices of the triangle A, B, and C. And then, again, the conventional way of naming a right triangle here is to name the side lengths with the corresponding lowercase letter across from the angle that's named with the same letter. So for example, if this angle up here is capital A, then the side across from it, which would be this side over here, we would name lowercase a. So that's the convention. Anytime we talk about the side that's lowercase a, that means that it's always across or opposite from angle, capital A. And over here on the right, if we've got angle B, then across from angle B, this leg over here on the left would be lowercase b. And now the most important one is that if capital C is the right angle, that means that the side across from the right angle over here would have to be lowercase c. Now, let's just review our vocab a little bit from last year, guys. If your right angle is located here, the side across from that right angle, that's an important word in trigonometry right here, called the hypotenuse. The other two sides then are going to be called the legs of your right triangle. So that's where I come up with leg squared plus leg squared equals hypotenuse squared. But again, most people prefer a squared plus b squared equals c squared, which is fine as long as we know that c always has to be the hypotenuse. There's a million different proofs of the Pythagorean theorem. Hopefully you saw at least one of them last year in geometry, but this is Algebra 2. We're not going to take too much time going over that. We'll just say, yeah, we know that it's right. So let's use the Pythagorean theorem in a couple of problems right here. So I've got 3 for you right here, and in each case, 2 of the 3 sides of a right triangle have been given to you. We're going to try to figure out what x is in each case. So in geometry, hopefully you guys learned that we start every problem with a formula. Leg squared plus leg squared equals hypotenuse squared is what I like to use here, and then we fill in what we know. Here's your right angle, guys, which means that the 2 legs are the sides on either side of that right angle. So one of the legs is 21, we'll square that. The other leg is 28, we'll square that as well, and our hypotenuse is x, and we'll square that also. What I would do next, everybody, if I were you, is actually, even without being you, being me, I'm going to go to my calculator right now, and in one step, I'm going to type this all in at once. 21 squared plus 28 squared. No need to do each one of those individually. So I got a total then of 1,225 for the left side, and that's equal to x squared. And now we'll undo the square by taking the square root of both sides of that equation, and we'll get x equals, let me type this in now, the square root of 1225, works out to be a nice clean integer here. X is equal to 35, and that is how we do the Pythagorean theorem. Now a quick check there, everybody. Make sure the side that we're missing here, x, is our hypotenuse. That has to be the longest side in any right triangle. So the fact that I got 35 right here, which is obviously actually greater than 21 and greater than 28, it doesn't guarantee that I got the problem right, but it tells me I'm probably on the right track right here. Now, just for the sake of argument, if I got an answer like x is equal to 26, I would know right away that answer couldn't possibly be right because one of the legs is 28 and the hypotenuse would need to be longer than both 21 and 28. So just looking at it real quickly, it wouldn't guarantee you that your answer is right, but in certain cases, it might guarantee you that your answer is wrong. And you might see that in action moving a little further down the line. Let's take a look at example B here. So another right triangle, which we know because of the corner mark here for the right angle. It's not an assumption. And let's get started. Now again, I like to write leg squared plus leg squared is equal to hypotenuse squared. And now we fill in what we know. How long is one of the legs? Well, what makes this problem different than the last one is that the hypotenuse now is known. And it's the leg right here, one of the legs I should say, that's unknown. And this 5 is another leg as well. So one of the legs is x. So we'll put that right there. The other leg is 5. And again, guys, most people, when I ask this question in class, actually tell me to put the 5 squared first and then the x squared. Really doesn't matter which one goes where since we're adding them. Our hypotenuse is 10, so we'll square that. Now let's simplify what we can here, guys. We're going to get an x squared plus a 25 is equal to 100, and now we'll just subtract the 25 from both sides. So there's this little extra step you have to do right here when your unknown side is a leg as opposed to the hypotenuse. Here we're going to end up with x squared is equal to 75. Then we'll take the square root of both sides of the equation, and let's talk about where we're going to go here in Algebra 2. My hope would be that last year in geometry, your teachers got you used to the concept of putting your answers in simple radical form as opposed to decimals. We're going to continue doing that this year, and at least in theory, we should be better at this now than we were last year, although we did this a long time ago back in Chapter 6, if I'm not mistaken, everybody. 75 is not a perfect square. So what we're looking for is a perfect square that does divide evenly into 75. And if you remember your list of perfect squares, technically 0 and 1 are perfect squares, but they don't help us at all. But here we go. 2 squared is 4. 3 squared is 9, 4 squared, 5 squared, 6 squared, 7 squared, and so on and so forth. And of course, there's no end to this list here. We're looking for the largest one of those numbers that divides evenly into 75. And I tried to start you guys off with a pretty easy one here. 25, if you think about money, quarters and 75 cents, yeah, the 25 works. So that 75 breaks down into a 25 times 3. And now, the step that we usually skip is that there's a property of radicals that says the square root, or really any root, of a product can be broken down into the square root of each individual factor multiplied together. The square root of 25 times 3 becomes the square root of 25 times the square root of 3. And then we evaluate what we can. The square root of 25 is just 5. And we can't do anything with the square root of 3, so that just goes along for the ride, and the length of x then is 5 times the square root of 3. Now, just if we wanted to see for sure if everything was hunky-dory right here, I could go to my calculator and type in 5 times the square root of 3, and it would tell me that the decimal equivalent of that, you guys really don't need to write this down, is 8.66. All I wanted to make sure is that my x value here is shorter than my hypotenuse, and it is. Now, it would be an assumption on my part to say that x has to be bigger than 5. I agree that this leg that I drew up here looks like it's longer than this leg over here, but that is not an assumption we are allowed to make in geometry, everybody, that one segment is longer than another. So I feel pretty confident about this answer right here. I knew the answer had to be less than 10, and this one is. I thought it should maybe be bigger than 5, and it is also, but that one wouldn't stop me from thinking this answer was correct. So, I've given you two examples so far, and in the first one I was nice to you guys because we ended up with a whole number, an integer for our answer. And in the second one, this is going to happen quite a bit here, guys. We're going to end up with a non-integer answer that's going to have to be written in what we call simple radical form. And I wanted to give you guys one more example right here because this is a problem that if we look at right here, I'm going to tell you guys something that some of you might remember from last year, but I worry that a lot of you guys have no clue at all what I'm talking about. A problem like this can actually be solved without a calculator if you understand the concept of Pythagorean triples. So let's talk about what Pythagorean triples are. I don't think you need to write down a verbal definition in your notes, guys. I think you'll get it right here. Pythagorean triples are groups of three numbers that work with the Pythagorean theorem. Okay, the first of which, hopefully this will ring a bell, guys, is a 3, 4, 5 Pythagorean triple. Now, I'm just going to explain one of them. What this means is that there is a right triangle that exists with legs of 3 and 4 and a hypotenuse of 5. Let's test that. Legs squared, so 3 squared, plus legs squared, 4 squared, equals hypotenuse squared, 5 squared. 3 squared is 9, 4 squared is 16, so that gives you a 25 on the left side, equals 5 squared gives you a 25 on the right side. And of course, 25 equals 25, check. So 3, 4, 5 is our first Pythagorean triple because it's a group of three integers that the Pythagorean theorem works on. Okay, there are four more, guys, that I always ask my geometry students to know. For Algebra 2, you guys don't need to have these memorized. You don't have to use them, but I am going to tell you it'll make your life a little bit easier. The second one is 5, 12, 13, followed then by 7, 24, 25. The fourth one that doesn't really follow the pattern of the others is 8, 15, 17. And the fifth one is 9, 40, 41. Now, I want to be real clear with you guys. These are not the only 5 Pythagorean triples. In fact, there's an infinite number of them. But the numbers get so big so quickly that they're not really all that useful to us. So, back to what I said a while ago, a problem like this can be solved without using a calculator. Let's talk about how. Now, the first thing you would do here is look at the 24 and the 51, and then go look at your list right here of the 5 Pythagorean triples. And I'd be looking for one with a leg of 24 and a hypotenuse of 51, and we don't have one of those. But what you might notice instead then, guys, is that the two numbers that are given here, the 24 and the 51, have a common factor of 3. They're both divisible by 3. So here's what I like to do. I like to write that common factor of 3 in the middle of my triangle, and I like to circle it. And then what I like to do is divide. I like to take 24 divided by this 3 here, which gives me an 8. And I like to put that near the 24, but inside the triangle. Now I do the same thing with 51. 51 divided by 3 is 17. So now, if I take a look at my 5 Pythagorean triples, now I'm looking for one that has a leg of 8 and a hypotenuse of 17, and sure enough, that's this one right here. Now that tells me, without doing any work, that this third side, the second, the longer leg, would have a 15 here, but I'm writing that in blue inside of the triangle. To actually figure out what x is, everybody, we are now going to multiply out. We're now going to take 3 times 15 right there, and we're going to get x equals 45, and that's the length of that third side. Now, how could I check my answer? Real quickly, guys, I could try 8 squared. Nope, sorry, not that. We're using the outer numbers right here, so how about 24 squared plus 45 squared should equal 51 squared. Let's check that. So I'm going to go to my calculator and type in 24 squared plus 45 squared, and I get this big number of 2601, and then I get a 51 squared, which is 2601 as well. So other than checking my answer, I didn't need a calculator in order to figure out that x was equal to 45. So I think that's a fun trick. Pythagorean triples don't always work, but they could have been used on that first example right there. We could have divided out a 7, okay, and gotten a 3 and a 4 right here. Oh, and that looks like a 3, 4, 5 triple. 7 times 5 would have gotten us 35 for x, which is exactly what we got doing it the normal way. Triples don't work all the time. Like in this case right here, I could have divided a 5 out. 5 divided by 5 is 1. 10 divided by 5 is 2, but there is no triple in that list, guys, with a leg of 1 and a hypotenuse of 2. So if it doesn't work out with a triple, you've got to do it the hard way using the Pythagorean theorem. So just, keep these handy, guys, and they might save you some time and effort on your homework here on 13.1. Okay, so that's kind of a wrap on what I wanted to talk about first, which was a recap of the Pythagorean theorem. Now I want to move on into the second part of our notes here, guys, which is to talk about what we're really getting into in Chapter 13, trigonometric ratios. And you guys probably remember this goofy little mnemonic device from last year, SOHCAHTOA. It's a made-up thing. It's just kind of fun to say, but it reminds you what all of the trigonometric ratios, sine, cosine, and tangent actually mean. For the time being, guys, just ignore what's on the right side of this page. We'll come back to that in a minute. Okay, so let's have a little recap right here. All right, the sine ratio, and this will be the only time we ever write it out, but the full name of sine has an E at the end. We always just abbreviate it as SIN. Sine is a ratio in a triangle that means opposite leg divided by hypotenuse. So let's go ahead and write that out. Now, a lot of people forget the word leg here, and they just write opposite over hypotenuse. And that might get you in trouble once in a while. I think it's a good idea to write that. So let's talk about what it is that we are talking about here. In this triangle that I've drawn up on the right, again, let's name it conventionally. The two acute angles then are usually going to be capital A and capital B, and the right angle is usually capital C. Now, when we're talking about sine and cosine and tangent, it's always a matter of perspective. Think about the triangle as something physical that you are standing in, and you are either going to be standing at angle A or angle B. Technically, you could stand at angle C as well, but that confuses things a little bit at the beginning. So I'm going to say, okay, here's us, guys. We are standing right there at angle A, and the opposite leg is the leg of this triangle that is across from you all the way on the other side. So this one right over here would be the opposite leg from where we're standing. And the hypotenuse is the hypotenuse. There's only one hypotenuse in a triangle, and it doesn't matter where you're standing. The hypotenuse is always across from the right angle. So this piece over here would be the hypotenuse. Okay, let's move on to cosine. That's the ka of SOHCAHTOA. Cosine is adjacent leg over hypotenuse. So adjacent leg, and again, I think that word leg is important. I'll show you why in just a second, over hypotenuse. So if you're still standing at angle A, the adjacent leg, now remember guys, there's two legs of a triangle, this one here and this one here. Opposite means across from you, but adjacent means next to you. So the adjacent leg is this one right over here. So adjacent means next to, and this is your adjacent leg. And the hypotenuse, again, is the hypotenuse right over here. The reason I think that the word leg is important here, guys, is because if that wasn't there, if you just thought cosine was adjacent over hypotenuse, this side right here, you guys, is also adjacent to where you're standing at angle A. So you got to be a little bit clear. There's actually two adjacent sides, but only one of them is a leg, and that's why I like the adjacent leg right there rather than just adjacent over hypotenuse. And the last one here, guys, tangent. Tangent is opposite leg over adjacent leg. So let's write that one out. Opposite leg, gotcha, divided by adjacent leg. So it's really just using two pieces that you used before. That's what tangent means. Now, I'm kind of jumping the gun here just a little bit, guys, but here's something you did not learn last year that you are going to learn this year, although we're not really going to use it much in this section. These are the three basic trigonometric functions or ratios: sine, cosine, and tangent. However, there are three more that you guys didn't learn last year, so let's real quickly define what they are. The good news is, though, guys, these three are called the reciprocal trigonometric functions, and all they are, as the name says, the reciprocals of the three that we just talked about. Cosecant is the first one, guys, written right over here, and cosecant is just the reciprocal of sine. So if the sine ratio is opposite leg over hypotenuse, then cosecant is just going to be the hypotenuse over the opposite leg. It's really not anything new. It's just a different way of writing it. Okay, and in higher levels of math, these things actually have some purpose to them. I don't know how much of that we're going to see this chapter, certainly not much in this section. Secant, then, everybody, right here is the reciprocal of cosine. So since cosine is adjacent leg over hypotenuse, secant will be the hypotenuse divided by the adjacent leg. And cotangent, this one at least makes sense, cotangent is the reciprocal of tangent. So that one will be the adjacent leg divided by the opposite leg. So that is a quick definition, guys, of what all 6 trigonometric ratios mean. So I want to walk you through a lot of what you're going to see on your homework here in 13.1, which is to take a look at a triangle like this and try to give them, it looked a little funny when that printed up here, and to try to give them a fraction right here for each of the 6 trigonometric ratios. So find the values of all 6 trig ratios of angle A. So that's what's important here, guys. So angle A is this angle right here. That is where you're standing, everybody. That's pretty important. So we're going to try to give them 6 fractions right here using those green letters, lowercase a, lowercase b, and lowercase c. So the first one we want, the sine of angle A. Now again, it's not a bad idea as you guys are getting started to write out SOHCAHTOA at the beginning of every one of these problems that you're going to do. Hopefully once you get the hang of this, you won't need to write that out. But for starters right here, it's probably a good idea to get that. So we want sine, and sine is the opposite leg over the hypotenuse. So from your position here at angle A, the opposite leg is across the triangle from you. That would be lowercase a, and the hypotenuse is always across from the right angle. That's lowercase c. That's all we can do with it in this problem, guys. The sine of angle A is little a over little c. Let's keep going. Cosine of angle A. Cosine means adjacent leg over hypotenuse. So from where you're standing, the adjacent leg is right here. That would be b, lowercase b, and the hypotenuse is still lowercase c. And lastly, tangent is opposite leg over adjacent leg. So we already defined both of these things in sine and cosine. From your spot at angle A here, the opposite leg is lowercase a, and the adjacent leg is lowercase b. Now that's something you guys learned how to do last year. This second column is new, but as I said earlier, this is going to go pretty quickly. Cosecant, and there's a reason we write it in this order, guys. Cosecant of angle A is just the reciprocal of the sine of angle A. So instead of a over c, cosecant becomes little c over little a. Nothing hard about that. Secant of a is the reciprocal of the cosine of a. So instead of b over c, this is little c over little b. And cotangent of a will be the reciprocal of tangent of a. And that one then is going to be little b over little a. And that's it, guys. That's all we would have to do in a problem like this. Now, it will get a little bit tougher. Let's look at a second example here, guys. And in this problem, I didn't just give you letters right here, little a, little b, little c. I've given you an actual triangle right here, but just to be mean, I only gave you 2 of the 3 sides that are in that triangle, a leg of 4 and a hypotenuse of 5. Now, one of the things that I'm really hoping you guys learned last year and that you remember from last year is this. Anytime in a right triangle, if 2 of the 3 sides were given to you, you can find the third side. And in fact, this one isn't really going to take us any work here at all. With a hypotenuse of 5 and a leg of 4, if I go back to my notes here just a little bit, right here, guys, we're dealing with a Pythagorean triple of 3, 4, and 5. And if I didn't know my Pythagorean triples, I'd have to do the Pythagorean theorem, and I guarantee you'd come up with a 3 here for that third side. But this is an example of where life is much, much easier for you guys if you know your triples. All right, guys, the sine of angle A, again, not a bad idea to write out SOHCAHTOA at the beginning of each problem right here. Sine is opposite leg over hypotenuse. So from angle A, here's where you're standing right there. Opposite leg is 3, hypotenuse is 5. There you go, 3/5. You don't need me to tell you this, guys, but I'll say it anyway. If that fraction could be simplified, you would need to do that in order to get full credit. Like, for example, if your opposite leg was 12 and your hypotenuse was 16, you would need to divide a 4 out of there and get 3/4. If you gave me this answer right here, I'd probably just take off half a point, but we don't want to give up any points at all. So always simplify your fractions if you can. Cosine of angle A, cosine is adjacent leg over hypotenuse. So the adjacent leg now is 4 and the hypotenuse is 5 as well. Tangent is opposite leg over adjacent leg. So again, from angle A right here, the opposite leg is 3 and the adjacent leg is 4. And now that we've got the 3 basic trigonometric ratios, the reciprocals should be pretty simple. Cosecant is the reciprocal of sine, so that'll be 5 over 3. Secant is the reciprocal of cosine, that'll be 5 over 4. And cotangent will be the reciprocal of tangent, which will be 4 over 3. Okay, not all that difficult. But of course, I have one more for you, and I did need to make life even harder at this point right here. So at first glance, this doesn't seem much different at all from what we just did. But what's harder now, guys, is that, again, only 2 sides have been given to you here, but I'm pretty sure this one is not a Pythagorean triple. I wouldn't write this down, guys. If you divided out a 2, which you could do, 10 divides by 2 to make 5, 12 divides by 2 to make 6. There is no Pythagorean triple, you guys, with a leg of 5 and a hypotenuse of 6. So as I told you, Pythagorean triples are great when they work, but they don't always work. So now we've got to do the Pythagorean theorem, guys. Leg squared plus leg squared is equal to hypotenuse squared. So one of the legs, we'll just go ahead and call that x. The other leg is 10, and the hypotenuse is 12. All right, let's simplify what we can. X squared plus 100 is equal to 144. We'll subtract the 100 on both sides and get x squared is equal to 44. And then we'll take the square root here and the square root here. And we'll get x equals. All right, guys, this one isn't too bad to simplify. What perfect square divides evenly into 44? 4, and it goes in there 11 times. I like to circle my perfect square and then bring not that number, but the square root of that number out in front. The square root of 4 is 2, and then the 11 just gets stuck under the radical. So this missing side here is 2 times the square root of 11. Okay, so unlike A and B, we had to do a decent amount of work right here just to figure out the third side in that triangle. Now from here, hopefully things won't be that bad. Sine of angle A. So again, you're standing here at angle A. Sine means opposite leg over hypotenuse. My opposite leg is 10. My hypotenuse is 12. But this is what I warned you guys about just a minute ago. You've got to simplify your fractions. Let's pull a 2 out of both the numerator and the denominator, and we'll get 5 over 6 for the sine of angle A. Okay, cosine now. Adjacent leg over hypotenuse. Our adjacent leg is what we just had to work to find. 2 times the square root of 11 all over 12. But just like the answer we came up with above for sine, you can simplify here. This 2 and this 12 can both be divided by 2. Now the 11 there, guys, is protected by the radical. Even if that 11 were a number that was divisible by 2, we wouldn't do it. We're just dividing coefficients. So when we divide a 2 out, that numerator becomes 1 times the square root of 11, or just root 11. You don't need to put the 1 there, and the 12 on the bottom becomes a 6. And you can't simplify that expression any better than that. Root 11 over 6. Now, tangent of A is going to throw something new at us, though. Tangent of A is opposite leg over adjacent leg. So from angle A, the opposite leg is 10, and the adjacent leg is 2 root 11. Now, 2 things. First of all, yes, you can divide a 2 out here and here, and you should do that. This becomes a 5 over the square root of 11. But now's the time we got to explain a concept that, again, I believe we talked about back when we were doing radicals. We are not allowed, as a general convention, guys, to leave radicals in the denominator of a fraction. So here's what we do. It's a process called rationalizing the denominator. 5 divided by the square root of 11 now gets multiplied by that ugly denominator, root 11, over itself. Now the value of root 11 over root 11 is just 1. So we're not changing the value of this fraction, guys, by multiplying it by 1, but we're putting it in just a different form. So 5 times the square root of 11 can't be simplified at all. It's just 5 root 11. But down on the bottom, root 11 times root 11 is just 11. Now that's ugly, guys, but what it has is that the denominator of this fraction is a rational number right there. So that is what we would consider a rationalized form. Okay, so there I've circled the values, the final values, for sine and cosine and tangent of A. Now the reciprocals, everybody. Cosecant of A will just be the reciprocal of sine, so that one's easy peasy. That's just a 6 over 5. Gets a little harder now. The secant of A is the reciprocal of cosine. That'll become 6 over the square root of 11. But that's exactly the same problem we just dealt with here in tangent. We can't leave a radical in the denominator, so we're going to multiply both the top and the bottom by the square root of 11. And that's going to become 6 root 11 over root 11 times root 11 is 11. Okay, so that's the value of secant. Now, for cotangent, this can either be really easy or pretty hard, depending on how you want to do it. The hard way, I wouldn't write this down, guys, is to say, okay, here's my answer for tangent. Cotangent is the reciprocal of that, which is 11 over 5 root 11. Now, that's not wrong, what I've just done, but now there's a radical in the denominator, so I would now need to multiply both sides by root 11, and this gets a little bit messy right here. Let's talk about the much faster way to do it. This was my final answer for tangent, but it was not my original answer. My original answer for tangent was right here that we then had to spin around. But if I took this original answer, this would actually be much easier than to reciprocate, because it's going to put the square root of 11 up on top and the 5 on the bottom. And that one now already has a rational denominator, so we don't need to go any further than that. So these then are the values of cosecant of A, secant of A, and cotangent of A. All right, guys, we're making good progress in this section right here. I'm going to stop this video right now and talk then in just on the next one about what we're going to do with special right triangles and trigonometry, and then eventually we're going to start solving triangles here and coming up with missing sides, but we'll do that in the next video. Okay, so that's a wrap on the first half of 13.1.